Right, okay, so the general, like a real abstract view of the CPU. So we've got CPU, which is a big old box. We're just gonna put a box saying registers or regs. We've got the ALU, so I'm just gonna put the major components down, and we've got the control unit. Right, so connected to the CPU, we have got our storage, our main or primary stores, our main store. Right, main store comprises of what? RAM. Cache. So that's our quick RAM, remember? So we've got cache. Remember, in reality, there may be no cache. You know, old school CPUs never had cache at all. You could still implement a cache system, and then some CPUs have multiple levels of cache, level 1, level 2, level 3, and they're all a little bit further, and as they get further away, we tend to make the caches bigger. But, God, logic nightmare.
Level 1, like, on the CPU?
Yeah, it's on the same chip, die. So you can't really get much closer. So when you see like a picture of a chip, you'd have like a great deal of it would be the cache, and then you'd have all the logic of the CPU with it or whatever. Yeah, so we've got RAM, cache. There's one other element of main store.
Is it ROM?
Yeah, ROM. Remember, you need that ROM because it's got to have some form of at least bootloader device or something in there, just to get everything going. Okay, so they're connected via a two-way bus and a one-way bus. And it's the one-way and two-way that tells you which is which. So which is the one-way?
Address.
Yeah, the address bus, because it's just there to select, so you don't need to get any data back. Now remember, this is a von Neumann machine that we're generally talking about. So we've got one execution unit and one connection to thing, but we'll talk about the differences between the two in a minute. The other one is the data bus, and it needs to be two-way because you need to be able to read and you need to be able to write. What else have we got connected? What else? There's two things connected. I'll draw them this way. There's two things that are connected to the control unit. One that goes in and one that goes out. How does, right, let's pose it this way, this question. How does the control unit get things to happen? So how does it issue a read? How does it tell the memory data register to transfer its value to the memory address register? How does that actually physically occur? What's the mechanism for saying, oi, move that data?
Control bus.
Yeah, control bus. So we send signals to cause things to happen. Okay, so the control unit has got an overview of what it wants to do, and it says, right, that needs to happen, that needs to happen. It does that by sending signals down the control bus. Obviously very quick. But it's governed by what? And that's the input. There's an input that governs the control unit that says, oh, get on with your job. Clock. The clock says, get on. That's why on old computers, the clock used to be fixed, decided by a crystal. Okay? Crystals are interesting because if you pass a certain current through them, different crystals will resonate with a very, very, very regular frequency, which is quite handy for the electronics industry. Quite a weird thing. But on modern computers, the clocks can be messed about with, which is why we get throttling. So the heat management systems can like turn the clocks down, so slow the computer down. Or Apple can slow the computer down by changing the clocks and pretend you're trying to preserve the battery. Not that you're trying to make people's phones slow so you can tell them a new one. Everyone does that. But anyway. Right, so there's one other external thing that arrives at one of the registers.
to do with interrupt.
Yeah, it's the interrupts. So they're in this like really like simplistic model of the CPU. Okay. They will ask you about the buses. Remember, they're just transport systems. What do they transport? Data. Even the control bus signals are data signals, really. But obviously the data's got specific jobs. Control bus is to configure equipment so that things can happen. Data bus is for reading bytes, whatever they are, instructions or data. Address bus for transmitting addresses. So the other thing that we talk about when we talk about the two buses is bus width. They tend to start asking about this, but you need to understand it. It's important. Right, so if we talk about the address bus first, what does the width determine? What do I mean by the width?
How much it can...
How many bits? So if I've got an 8, you wouldn't have this, but if I've got an 8-bit address bus, so this ties back to all that data representation stuff. If I've got an 8-bit address bus, how many different addresses can I specify?
$256?
Yeah. So with an 8-bit, you can only address 256 bytes. So that's rubbish. So 256 bytes addressable. Uniquely addressable. What if you had 16 bits? Give me an approximation. I don't need the exact, I know the exact value.
You get the exact.
You can do it exact.
2 to the power 16.
But it's 2 to the power 16 or 64K. So 64,000. That's getting a bit more useful. What if you've got a 24-bit address bus? Which you do get.
So it's not, I can't do this.
You should know these approximations. That's about 16 million approximately.
Oh, I'm trying to get the exact.
What about a 32-bit?
2 to the 32.
Oh, you should know some of these numbers. You're shaming yourself, Anonymous, too.
What I mean?
I can say things like that now. It's good. I couldn't say that if I hadn't said your name. 4 billion. Or what we might describe as 4 gigabytes. That used to be, on the 32-bit processors, the limit of the address bus, which is why you couldn't, on older Intel PCs, put more than 4 gig of RAM in them, because they were restricted to 32 bits. Now, if you think, when we talk about a 64-bit CPU, we're not talking about the address bus, we're actually talking about the data bus. Okay? Because they never really talk about the address buses until you try and put more RAM in and you go, oh, I can't go above that. If I had an 8 gig limit on my line, how many bits would it be, the address bus? If I had 8 gig. Right, if 4 gig is 32 bits.
64.
What?
No, actually. Well, yeah, 6 exponentials, isn't it? We just...
It goes up by 2.
Yeah.
So it'd be 33 bits,
Yeah.
isn't it? So 33 bits would be,
I forgot how maths worked there.
oh, would be 8 gig. 34 bits. Now this isn't like the data bus. Data bus we tend to stick with powers of 8, but because the address bus is slightly different purpose, we're just saying like how much do we want to be able to address. So that will allow us to have 16 gigs. If you've got 35 bits, you can go up to 32 gig, etc., etc. But one of the things you've got to be careful is when you're designing these circuits, you've got to have space to put all these lines. So you need, for each one of those bits, you need a line, which is why if you look on a motherboard, you get these tracks that are all close together and they're the buses. But they don't always necessarily stay together. They might have to go around chips and underneath and through different layers of the circuit board and everything. Right, so with the address bus, you can have non-uniform. So you might find that you've got 11 bits or 12 bits or 13 bits for the address bus. But it just determines how many uniquely identifiable bytes you can refer to. Okay. With the data bus, the width, same thing. It's how many bits, but in this, so it's how many bits can transfer at once. So if you've got a 4-bit bus, you can transfer a nibble at once. And we did have 4-bit CPUs. Okay, so you can transfer a nibble, which you all remember is 4 bits. 8 bits, you can transfer a byte. So when we say we've got an 8-bit computer, we actually mean the data bus, generally. So that's transfer a byte. 16 bits. 16 bits and above, we tend to simplify this and we call it a word. We call it the word length of the computer. We call it a word. Okay, so you have 16-bit words, 32-bit words, and what we've got now, which are 64-bit words. So the thing with 32-bit and 64-bit, so that one, how many bytes are actually getting transferred in one transfer from memory? With 64 bits, how many bytes?
8.
Yeah, that's 8 bytes in one go. So if you're processing an array, actually, you could read, you might only want to read 1 byte. So you actually, to read 1 byte on a big fat bus, you're actually bringing another 7 that you didn't want. So there is an efficiency thing. So 16 bits is a nice sweet spot, but if you look at a lot of programs, when we're programming in C# and a lot of languages, 32-bit is the standard integer size, even if we're writing for a 64-bit machine. Because generally you don't want to use 64 bits because you're wasting twice as much memory space. It's one of the reasons, these big fat buses are one of the reasons why programs take up more space and data takes up more space, because you use these big fat formats when actually we're only storing the number 3 and 2 or something like that. You don't need 64 bits to store the number 3 and 2, but the program, every time you use int, you're using 32 bits, even if you're only counting to 10. You can change that in your code. You can put int 8 and things like that. You can put byte or whatever. Okay, so you might get asked about the bus widths. So if I need to read 8 bytes from memory on a 64-bit bus, that's 1 fetch. If I've got an 8-bit bus, that's 8 fetches. So there is an efficiency saving by increasing, but you just can't keep going because you've got to be able to route it all on the motherboard. You know, I think once you start, even if you look at the graphics cards, and you look at, they're going, we've got 384-bit bus and things like that. Well, they haven't. What they've got is they've got multiple ways of they've got synchronous transfers and things like that. They haven't actually got 384 tracks dedicated to the data bus. So they're like synchronous concurrent reads and things like that. Any other questions about the data busy stuff and the externals?